Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones. Today we're doing multivariable calculus. We're in chapter 2, double and triple integrals. Double integrals over general regions is what we want to do today. And specifically what we're going to do is we'll give the definition of a double integral over a general region D, and then we'll discuss type 1 and type 2 of these types of regions. In one dimension, you don't have very many options. Now we can have all kinds of regions D, and how the heck are we going to define that? Actually, in our picture, that's the idea. What we already know is how to define the volume under a surface and above a rectangle. Then what we do is just make sure that weird region you have is inside a rectangle of some kind, and then we just restrict our surface to being 0 outside that function inside that region. Let's do it. So double integrals over general regions will give the sketch of how we actually derive this idea. What we're trying now is when we had a surface which was the graph of a function of two variables, we wanted to know what the volume of the object was by taking the volume below the object, which was the surface S, and above a rectangle R. Now what we're saying is if we already had that scenario, what if I wanted to do some general region and not some rectangle? I've already drawn it in, but suppose you had just some orange region D, and we want to know what is the volume below the surface, which is the graph of F, but now above D, not a rectangle. What the clever idea is, in long story short, we're just going to create a function where we find any rectangle that completely contains D. It doesn't matter which one, you could take any other one. This one will suffice too. It didn't matter which rectangle I pick, but as soon as I have a rectangle, ooh, that was close, but as long as it's completely contained in there, we can do this idea. What we're going to do is we're going to create a big function, f of x, y, which is little f of x if x, y is in the region D, and then we're going to say it's 0 if x, y is in R. Technically, that's remove set minus. So we're saying it's in the other part. Now I drew on there. I screwed it. Now cleverly, how do you set up what the boundary of that region D is? What you're going to have to think yourself, because we now have that the double integral over the region D of f of x, y, dA, we're cleverly now defining as the double integral over a rectangle, which we do know how to define using Riemann sums, of big F. And this seems reasonable because when we compute this double integral, what that's saying is to compute the double integral over that arbitrary region D here, if we do the double integral over the rectangle of large F, that means it's over the surface little f over the rectangle, but there will be no surface there outside of D. And so that makes sense that it should be this definition that we get. And you can prove that it is. This is double integrals. Let's try that. We're going to get two main types of double integral regions that we're going to integrate, type 1 and type 2. That basically will look an awful lot like calculus of one variable when we do area between curves. You can have an upper function y equals f or g1 of x and a lower function g2 of x, or you can have a left and a right function x equals h1 and of y, or x equals h2 of y, and then you have to take upper minus lower or right minus left, and you get area between curves. Now what we're going to do is we're going to have to set up those same regions, so it's going to look an awful lot like single variable calculus when you do this. But now what we're going to do is those pictures, we're going to set up that arbitrary region D, and then we're going to find the volume of the surface over that thing instead of finding the area between the curves. So it's going to look an awful lot like area between curve setups. Let's do that. We're going to consider two main regions types. Type 1 region is going to be, if we can phrase the region as going from two vertical lines x equals a to x equals b, and then having that our region is stuck between two functions y equals g1 of x and g2 of x, then we are going to get that the double integral over the region D of f of x, y, dA is going to be the integral from a to b of the integral from g1 of x to g2 of x f of x, y, dy, dx. And so this is also known as the first statement in the strong Fubini's theorem. You're basically doing iterated integrals, but now what we have is we have one of the limits are not constants. And if you want to interchange these, you're going to actually have to sketch the region and then rephrase. If you can invert the functions, and then you can rephrase y equals f of x or x equals g of y and rephrase this, but that'll be the type 2 regions when we have, instead of doing this, sometimes it's easier when you have functions that go this way like brackets. Then I can consider those because those are not graphs of functions technically, and we'll do the other type. Let's do an example of this type 1 region. Example 1, we want to compute the double integral of sine x over d, where d is the region, which is the triangle in the xy plane bounded by the x-axis, the line y equals x, and the line x equals 1. Good. This one I sort of picked on purpose because this is the hardest part. They give you now a horrible English sentence and you have to unwind what that means. You have to draw the picture so that you can see what the region is. I'm not going to give you the craziest questions, especially on exams, but when you're doing these and you get some practice problems and you get the craziest ones, then yeah, it's really hard to set these things up because you can't picture how to draw these things. And then we go up a dimension and then it gets even worse. So when you can, please draw them. These ones are basic lines of the x-axis. Every time I draw the Cartesian plane, I know how to draw him. I know how to draw the vertical line x equals 1, and I'm pretty sure I know how to draw y equals x. So let's do that, and then we get an idea of what our region looks like. It's a triangle. They're saying it's this guy. It's the line x-axis, turns out, first of all, that guy. Then the vertical line x equals 1, probably up to there somewhere. No, where does 1 and 1? Close enough. And then it says the line y equals x. Is the line y equals 0, the x-axis. They're kind of mean. That's where they're also hiding. That means y equals 0, x equals 1, and y equals x. I got 3 lines. They've given me 3 rectilinear lines, essentially. From that, now, I can see that this is the region D. What do I want to do with that? Now that I have that, I want to say to myself, by the time you're on an exam, probably, you're going to say, do I phrase this as type 1 or type 2? Luckily, we just did type 1 only, so we know we're going to phrase it as type 1. And what do? That says, I see that, where does x go from? X goes from 0 to 1. And then I also see that, where does y go from? Y is going from the function 0, luckily this time, to now the function which is not a constant, but is the line y equals x. And then once I have those, now I can use the stronger version of Fubini's theorem to compute this double integral. And that says that the double integral over d, which is this triangle, of our function sine x over x dA can now be computed as the integral from 0 to 1 to, and the integral from 0 to x of sine x over x dy dx. And now specifically, where I put the brackets even for myself, I've done it a bunch of times, I still do it. That means I'm holding x constant, and then I'm going to integrate with respect to y. That gives me the integral from 0 to 1 of sine x over xy evaluated from 0 to x dx. Luckily, I've got the bound 0, so I'm not even going to put it in there. When I put it in there, I get 0. So this gives me the integral of sine x over x times x dx. Cancel, cancel. From 0 to 1. Don't forget your limits. What does that give me? That gives me the antiderivative evaluated from 0 to 1 of sine x, which is going to be negative cos x. Did I do that right? I can't remember. Take the derivative of this. Negative sine. Okay, yes, I got that right. And that is going to give me negative cos of 1 minus negative cos of 0, which is 1 minus cos of 1, which is 1 minus 0.86, I think, something, which is probably going to be not equals, approximately equal to 0.46. Cos of 1. You eventually want to know what cos of 1 is. How are we going to do that? Power series representation, and then you get cos of 1. Next question. Cats. Got a couch she's going to lay on. She's going to hold the couch down for us. You hold that couch down. We're going to do some multivariable calculus. Type 2 regions D. Now what we can do is, if I can take a region and phrase it as being bounded by two functions, x equals h of y, 1 of y, and x equals h2 of y, between some vertical values, y equals c to d, then what we can do is we can say c is less than or equal to y is less than or equal to d, and then h1 of y is less than or equal to x is less than or equal to h2 of y. And again, just like when we do area between curves, we could phrase it the first way or this way. And now what are we going to do with this? Now we can say, by the stronger version of Fubini's theorem, we can say that the double integral now over the region D of our function f of x, y, dA can be written as the integral from c to d of the integral from h1 of y to h2 of y of f of x, y, now dx, dy. This is how we're going to compute double integrals of functions of two variables over arbitrary regions, and if they're positive, interpreted as volumes, by phrasing the second type of region we're going to have, where we've had to phrase the functions as x in terms of y, not y as functions of x. Let's do an example of this one. All right, example 2, doing this of the second type region, we're going to compute this double integral over this paraboloid, where we have a region D, which is bounded by, it says, the line y equals x, and the parabola x equals y squared minus y. So technically that's not a function in the plane as I classically do it, but it's this curve nevertheless. How we're going to phrase that? We now know that because inverting this is going to be awfully hard, we're going to phrase and want to phrase our functions as x as two functions of y. And then we have to sketch these, and this is a little bit harder also. So first of all, what am I going to get? I want to try and sketch these things in the plane. And we're used to doing it this way, but now we're interchanging the roles. So what does that look like? Well, this one, luckily, I know what that one looks like. So let's do that one. I'm going to get that, I'm going to guess. Even though technically we're interchanging the roles of that. So that's now the function x equals y, which is y equals x. Commutative of the equal sign. Who's the other one now, though? The orange one we want to draw. Uh-oh. Okay. This is x equals y squared minus y, which is y squared minus y plus 1/4 minus 1/4. What? Yeah. B is -1 divided by 2 is -1/2. Squared is 1/4. I need 1/4, but adding 1/4 is crazy. Instead, I'm going to add 0, my favorite dirty trick, to complete the square. This is now a completed square. This is y minus 1/2 squared minus 1/4. Now that's a parabola in standard form, but as a function of x in terms of y. What does that give us? The vertex is now what? 1/2. Y is 1/2. X is -1/4. So doop doop doop. Y is 1/2, x is -1/4, not to scale. And so that's going to give me the vertex right there. Ding a ding a ding. I should have drawn it in orange. This is going to give me this guy, I believe. This is what we want. What I needed from that was, this was x equals y squared minus y. It doesn't have to be a perfect sketch either, but what I want to notice from this is, where am I going from? And you can also set those equal to each other coincidentally. How do I do that? Where will they intersect? I take that one calculation to help me sketch, but where does that happen? Where does this happen and this happen? How did I suspect it was going to happen? Well, I've drawn this a bunch of times before, and I prepared myself, but I have to say, when is x equal to y squared minus y? And so that's going to give me y squared minus 2y equals 0 if and only if y equals 0 or y equals 2. And therefore, we're going to get 0 and 2 is where they are going to intersect. That's all I need. I don't really need to figure out the x coordinates because now what does that say? That says 0 is less than or equal to y is less than or equal to 2. And x now is who is the left and the right one. That's why I had to draw my picture to make sure. But now it's from here to here. So it's going to be x is between y squared minus y is less than or equal to x is less than or equal to y. From this information, what we're going to do with that now is we have our bounds and we can use the Fubini theorem again. This tells us the double integral d of 3x squared plus y squared dA can now be written as the integral from 0 to 2 of the integral from y squared minus y to y of our function 3x squared plus y squared dx dy this time. That is going to equal the integral from 0 to 2 of, we're holding y constant and computing with respect to x. That's going to give me x cubed plus y squared x, evaluated from y squared minus y to y dy. Once I put those in there, we'll have no more x's left. This is equal to, now I use the fundamental theorem of calculus part 2 and I evaluate these. I get the integral from 0 to 2 of y cubed plus y squared times y minus y squared minus y cubed plus y squared times y squared minus y dy. Simplifying this, we get equals the integral from 0 to 2 of, here what do I get, y cubed plus y cubed, which is 2y cubed I guess, minus this one by the binomial theorem, the power, it should be 1, 3, 3, 1, and then the sign should alter, and then I should start at 6 and then go down to 3. So this should be y to the 6 minus 3y5 plus 3y4 minus y cubed, and then plus, here I'm going to get y to the 4 minus y cubed bracket dy. We're going to have to move it up again. Need a bigger board, it turns out. Equals the integral from 0 to 2 of 2y cubed now. And then what do I have? Can this be combined? Yes, let's just make this combined. That should be a 4 now. You saw me do it. And then this one is what? I get minus minus, right? Minus 2 dy equals, I simplified it even more. So then I'm going to get minus y to the 6 plus 3y to the 5 minus 4y to the 4 plus 2y cubed. And then there should be, these ones are going to double up dy, so let's move that to the top. Moving that up and simplifying one more time, I get this is the integral from 0 to 2 of, and then writing it this way because I have OCD, I'm going to write this as negative y to the 6 plus 3y to the 5 minus 4y to the 4 plus, and then these guys can combine to give me 4y cubed dy. Now I can take the antiderivative. That's going to give me, by the fundamental theorem of calculus part 2, I'm going to get negative 1 over 7 y to the 7 plus 3 over 6 y to the 6 minus 4 over 5 y to the 5 plus 4 over 4 y to the 4, evaluated from 0 to 2. Cleaning that up a little bit more, that is going to give me negative 1 over 7 y to the 7 plus 1 half y to the 6 minus 4 over 5 y to the 5 plus y to the 4, evaluated from 0 to 2. Now doing this, evaluating, we get this is equal to negative 1 over 7, 2 to the 7, plus 1 half, 2 to the 6, minus 4 over 5, 2 to the 5, plus 2 to the 4, minus 0. Now from here, I can use probably a couple clever exponent laws. I see that this is going to be 2 to the 6 minus 1, so I can get 2 to the 5. And what is that going to give me? So here I get negative 128 over 7 plus 32, 2 to the 5, minus, again, 4 times this guy is 128 again, the power of 7 over 5, and then plus 16. So we're going to get that this is equal to 48 minus 128 over 7 minus 128 over 5, which is now going to be equal to something equally horrible, which is now, if I need a common denominator, I have to do 48 times 35 over 35 minus 128 over 7 times 5 over 5 minus 128 over 5 times 7 over 7, which is equal to dot dot dot. Holy crap, dot 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 equals 144 over 35 is what it is. Next time what we're going to do is we'll do more examples of computing double integrals over arbitrary regions of type 1 and type 2. Please subscribe right here and hit the notification bell. You'll get notification for this series and a bunch of other ones on our channel. See you next time.